Hello, my name is Samudrajit Thapa and I welcome you to the video abstract of our paper titled Leveraging Large Deviation Statistics to Decipher the Stochastic Properties of Measured Trajectories. Diffusive motion, as originally discovered by Robert Brown, is at the heart of many processes in nature such as molecular spreading in cells. In modern single particle tracking experiments and supercomputing studies, the observed stochastic motion typically feature deviations from standard Brownian motion, and we seek to identify the physical mechanism underlying the measured dynamics. Most of the current tools, such as Bayesian analysis and machine learning, to detect the underlying stochastic process of recorded time series, are technically involved and often incur large computational costs, with the cost increasing with the number of models considered. In this paper, we look at a simple yet efficient method to reduce the list of feasible models and thereby complement other methods. Our method is based on the large deviation statistics of a routinely observed quantity, namely the time averaged mean square displacement. As can be seen from the equation, it is the moving time average of the squared displacement along the trajectory at fixed time window delta. N is the number of points in the trajectory. Noteworthy is that the TAMSD is a random variable for finite measurement time, and it follows the so-called large deviation property for Gaussian processes. A random variable A, indexed by n, is said to follow large deviation property if the probability of A to belong to a set B decays exponentially with some rate function for large n. Often, what can be calculated is an upper bound on this probability. This is what we consider for the TAMSD normalized by its expected value and look at the probability of its deviations from unity by some arbitrary quantity epsilon. For Brownian motion, we find that indeed for the physically relevant case of n much greater than delta, the bound is extensive in n, and the probability of deviations decay exponentially. Moreover, as is seen from this figure, the bound divides the plot area into two regions. The gray shaded region is allowed for Brownian motion, while the unshaded region is forbidden. Indeed, simulated Brownian motion denoted by dots obey the bound and lie in the gray shaded region. Moreover, using this bound, we can distinguish between different stochastic processes as is seen in this figure for different simulated datasets. For a class of processes, the probability of deviations obeys the large deviation bound for Brownian motion and lies in the gray shaded region for the whole range of epsilon, whereas for another class, it exceeds the bound for some range of epsilon. This enables us to construct a decision tree like this, to rule out some models and arrive at a shorter list of feasible models. Analyzing experimental data, we could detect several interesting features such as anisotropic motion of the beads tracked in mucin hydrogels at neutral pH conditions, and short-time correlations in the climate data of temperature anomalies. For details, please have a look at our paper. Thank you.